Hello, it's Keith here, and this is lesson 2 of my 65816 assembly programming tutorials, in which we look at the new features of the 65816 processor, which most people know as the Super Nintendo processor. Now today we're going to be looking at the new addressing modes. The 65816 has all of the original 6502 addressing modes, but it's added a load of new ones as well, and we're going to be going through them today and trying them out on some emulated systems. But before we go into that, I'd like to tell you that I've written a book on 6502. This book doesn't cover the new 65816 functionality, but if you want to brush up on the 6502 content, my book will do that for you. It's available now on Amazon. It's called Learn Multi-Platform Assembly with Chibi Akumas, and it covers Z80, 6502, 68000, 8086 and ARM. So take a look at that if you're interested. Anyway, let's go over to today's example and let's see it in action. Now we're going to be trying various commands today and various addressing modes and see how they work. And to do this, we're going to set up some test data on the system. But because we're being quite brutal with the addressing, sometimes we're overwriting whatever's in specific memory positions to test effectively. These examples won't work the same on every system. So if you decide to try them on a system other than the one I show you, you may get different results. So just bear with me on that. It's an unavoidable fact for the kind of example we're doing today. So we've got various setup we're doing here, because the examples we're using today, we need some test data in place, and we've got some jumps here to jump to one of the examples, and the first we're going to look at is the direct page. So what are we doing? Well, the direct page functions initially as the 0 page did. So if you think of a 16-bit address, the top byte would be 0, and if you think of it as a 24-bit address, the top 2 bytes would be 0, and the bottom byte would be taken from the 0 page entry we were looking at. For example, this one here would be loading from memory address hex 80 in the 0 page, or the direct page if the direct page was at 0. But we can now relocate the direct page, and we can change that top byte of the 16-bit address. And so what we're effectively doing here is we're setting the top byte to 03 here. So we are now changing the address from a typical 0 page to a direct page starting at memory address 300 in hexadecimal. The way we do that is we load the 16-bit C accumulator with the address that we want to use for the direct page, and then we use TCD, transfer C, the 16-bit accumulator, to D, the direct page register. And so that has now set to the direct page. And then we've just got a program command here that is dumping the direct page to the screen. This is just a little test program I've got. And then what we're going to do is we're going to try loading the X register and the Y register from memory address 80 and 82 in the direct page. And if the direct page has changed as we expect, we will get the values from that dumped range. So let's see what happens. Okay, so here we've dumped our memory 000380 here, and you can see we've got 0, 1, 2, 3, 4, and what we've done here is we have loaded in from memory address 80 in the direct page, and our X register is loaded in 0100, and that's because the little endian value is there, and our Y register is loaded in 0302, and that's our little endian value just here. So you can see those have loaded in. And X has loaded in with hexadecimal 100, and that is our little endian value just there at 380, and the Y register is loaded in with 0302, and that's the little endian value just here. So it does indeed look like our direct page has changed, and you can actually see that being shown just here as part of the register dump there. The direct page is now at 0300. Now we can also confirm that if we change this and we change it to the more typical direct page of 0 here, and we run this again, well, now you can see that X and Y have got totally different values, because although the addresses we're loading from haven't changed here, well, that direct page is now back at the 0 address, so it's loaded in completely different values. So really, the direct page is just a 0 page that's relocatable. That's all it is. It's just got that extra flexibility for us. We do, however, have some new commands that we can perform on the direct page, and we'll take a look at a couple of them now. Now, what we're going to look at now is direct page indirect addressing. Now, in the past, we did have indirection options, but we had to use an index register, even if we didn't really want to. So quite often we'd have to set the Y register to 0 and things like that. Now, like with the 65C02, we can directly address indirectly parts of the 0 page, direct page now as it's called, without using any registers. So we can now use a command like this, where we don't want any kind of offset. So this will load in from the address at memory address 81 in the direct page. So let's see that in action here. So here we've loaded in from direct page entry 81 indirectly. Now at memory address 81 is the 16-bit address 0201, and if you see here we've dumped memory address 200 here, and you can see it's got 61, 62, 63 and so on here. So what we've done here is we have loaded the accumulator from that address, and you can see it has indeed loaded in 6362, which is the value here at memory address 0201, which was loaded indirectly from the direct page just here. So that has indeed worked. Now that's loading in from a 16-bit address, and that's because we've specified normal brackets. But the 65816 has new square brackets, and these specify a 24-bit long address. So this is actually loading in 3 bytes and using those 3 bytes as an address. So now we're loading in from 3-byte address at memory address 81 in the direct page. So that will be this address here, so 030201. Well, coincidentally, I've dumped memory address 030200 here, and you can see it's actually got 61, 62, 63 and 64 once again. Now, the reason for that is because of the Super Nintendo's memory layout. What we will do is we will actually try using a different emulator this time. We're going to use the Apple II GS emulator. It's because of the memory layout of that system. So this time we're now using the Apple II GS, and this time if we have a look, you can see now at memory address 200 we now have 40, 41, 42, 43, and this time at memory address 0302 we have 61, 62, 63, 64. If we load in from long address 010203 here from the direct page, we will load in our accumulator from memory address 030201, which contains the value 6263, and you can see that has been loaded into the C register just there, the 16-bit accumulator, by that command just there. Now we can also use an index. Here we've used the Y register as an index, so this will get the 24-bit address from direct page entry 81 in hexadecimal and then offset that by 1 and read the value from there. So this will get the address 030201 here. It will then add 1 to that and read in from that address, and so this will load in from not this address, it will load in from 302002, and this will get in the value 6364 in the little endian, which is 6463. So that's been loaded into the accumulator there. So the 65816 allows us much more flexibility with both the direct page, allowing us to relocate it and allowing us to address it in new ways, and it also allows us extra functionality with regards to the larger address space with long addressing, both directly, which we'll see in a moment, and with the direct page. And it's always these square brackets you need to see and be aware of. You know, if you use the wrong kind of bracket, you might end up with problems. But as I say, the square brackets do define long addressing, those 24-bit addresses being used in this case from the direct page. So there we go. So that's how we can use the direct page indirectly. Now, what we're going to do next is have a look at absolute indexed indirect addressing. Bit of a long name there. So let's have a look at this. Now, the first thing we're going to be looking at, and this command only works with jumps, and this will load in an address from a table, and in this case it will jump to that address. So we're jumping to the address in the table test jumps offset by X. So here we are setting X to 4, and that will offset by 4 bytes within our test jumps table, and our test jumps table has 3 word addresses which are different print routines, and each one just shows a different character to the screen. Not very imaginative. Print A will print an A, print B will print a B, and print C will print a C. So we've got a sort of vector table here, and we can jump to one of these just by loading X with 0, 2 or 4, and that will show one of the characters to the screen. So for example, if we just run this as is, and we'll go back to our Super Nintendo. Well, here we loaded the X register with 4, and 4 bytes offset from the start of test jumps is the print C routine, and so we have, unsurprisingly, printed a C to the screen. But if we change from a 4 to an offset of 0, well, now we're going to be reading in the first word in that table, print A, and so when we run this again, well, shock, we've printed an A to the screen. In case you can't figure it out, we are always working in multiples of 2 because each entry in our table is 2 bytes. If we use 1 or 3, we'd end up reading half of print A and half of print B's address. We'd end up running something totally crazy, and it would be, who knows what would happen. It would just depend on what happened to be at that address. So if we use an odd number like 1, nothing's happened, nothing's appeared on the screen at all, and we could have got crazy corruption and things. And that's how we can use an indexed indirect address, specifying the full address here, because we're specifying test jumps as a full address rather than using an entry in the 0 page. And as I say, that only works for jumps. What we're going to look at next is some new commands which use the stack as an offset. Let's have a look at these. These are stack relative commands. Now, these aren't something I tend to use very often, coming from Z80, but a lot of other processors tend to like pushing parameters onto the stack as a way of passing them to other subroutines. I've tended to become more familiar with using the registers themselves because Z80 has a lot of registers, but other systems do frequently push items onto the stack and then read them off the stack via offsets. So let's see this use of the stack in action. Okay, so what have we done here? Well, here what we've done is we've loaded a 16-bit value here into X, all these Fs, and pushed that onto the stack. And then we've loaded 1, 2, 3, 4 and pushed that onto the stack. And then we've loaded 5, 6, 7, 8 and we've pushed that onto the stack. So now we've got loads of values on the stack and we're loading X with 0 here. And you can see, if we look at our dump of the stack here, this is our stack. And you can see FF, which is our marker really for the start of the test data. And then we've got 1, 2, 3, 4 in little endian, 5, 6, 7, 8 in little endian there. So we've pushed those onto the stack there. Now what we're going to do next is we're going to load in, we're using the accumulator and using the stack as an offset, and we're going to basically add 1 to the current position of the stack pointer here, and we're going to load the accumulator. Now the current position of the stack pointer is at 01F9. And this is basically at this position here. So if we add 1 to that, we are going to load in from 5, 6, 7, 8. And you can see that has been done just here. We then load in from 2 plus the stack pointer, and we show the results again. Well, if the stack pointer is here and we add 2, then we're going to load in 3, 4, 5, 6. And you can see we've done that just here. And of course we could continue this if we just add another line here. If we just add extra 2 lines here and we put 3 and 4 and we do this again. Well, you can now see we've loaded in the 1, 2, 3, 4 and the FF12, and these have been loaded in off the stack just here. And of course the important thing to point out here is we've never had to transfer the stack register to X. We've never had to do any kind of addition or anything like that. We can use the stack pointer directly and we can read in values that were pushed onto the stack, and if this was in a subroutine we could read the values that were pushed onto the stack before the calling of the subroutine and use them in whatever way we wanted. Now in that example we were loading values directly from the stack, but we can also load indirectly from the stack. We can load from an address that was pushed onto the stack effectively, and that's what we've done here. In this example we're going to load in from the stack pointer plus 2 offset by Y, and we're loading Y with plus 1 here, and we will see that in action. So once again we're pushing 01, 02 and 03, 04 onto the stack here, and you can see those here, 01, 02, 03, 04 here. And then what we're doing is we are loading from the stack pointer plus 2, and so the stack pointer is basically pointing at this hexadecimal 80 here, so plus 2 we'll be pointing to this 16-bit 0302 value, which is memory address 0203 in Little Endian. And you can see we've dumped 0200 here, coincidentally. And then what we've effectively done here is we have added 1 to that address because y equals 1. So we've effectively loaded the value in from 0304 here. So that's 0300, 1, 2, 3, 4. So 65, 66 here is the value we've loaded in. And you can see that has been loaded into the accumulator here. Now we can test this if we just copy this data here and we change the y value to a 2 here and run again. And I would always suggest the point of this is you go to my website, you download the examples and you change them and you see how the values change to confirm this for yourself. I was not able to learn this kind of thing just by reading books on it, and you actually need to see it in action to fully let it sink in what's happening. So we loaded in values 65 and 66 here when y was equal to 1. Well, now y equals 2. So instead of loading in the value 65, 66 here, we've now loaded in 66, 67, and you can see that has been loaded in just there. So we can load in indirectly, loading an address off the stack and then loading in from that address offset by y in this case, which is very handy. Okay. So that's stack relative addressing. As I say, not something I would necessarily use so much coming from the Z80, but the next one is very much something that I would use. It's something that I suppose is noticeably absent from a great number of CPUs, really. The Z80 has a command called LDIR, which is load and increment, which sequentially copies bytes from one address to another. And now the 65816 has it too. It has MVN for move next, and MVP, not most valued professional, it's move previous. So we've got these two commands. Now these are in a bit of an odd format because we specify 2 bytes after the command. This is a bit of a rare format. Now these are the source bank and the destination bank, and the reason they're there is because the rest of the data is specified by the X and Y registers. The address, 16 bits of the address is specified by the X and Y register, but the 65816 is of course 24 bits, so that's not going to be enough, and the remaining top byte is specified here. So we're going to try these out, and we're going to transfer some data from bank 0 to bank 3, and we're going to transfer from test data, which is the data within our program, to the memory address 0 in bank 3. So that's going to be 03 quadruple 0 effectively. Now move next will copy A bytes in ascending order, whereas move previous will copy A bytes in descending order. So basically decreasing, move previous would decrease 1 after each transfer. And the reason we have 2 commands is if our ranges overlap and we use the wrong one, we would effectively end up filling the range because we would be copying the data we had just overwritten. So that's why we have the 2 commands, but they both work essentially the same. We specify the source with the X register, either the start of the range in this case, or if we're using move previous, the end of the range. And then we specify the destination, and then we specify with the move next or move previous commands the 2 bytes that are the top byte of the 24-bit address. Now the only thing to notice about this is that these commands both alter the currently active bank, the current bank register. So what we're doing here is we're using PHB and PLB to back up and restore the bank register, because otherwise our program would malfunction, or it almost certainly would. So let's try these out on the Super Nintendo. Okay, so we've got some test data we wanted to copy here. And so what we've done is we've shown the starting value of the 30,000 range, and it's just got some random data there. We don't know what that is, but we don't want it. And then what we've done is we've used the move next command to copy our test 8 bytes here. You see these being transferred here, and these have filled the first 8. And the reason they've filled the first 8 is we specified the accumulator to 7, and that specifies the bytes to copy -1. So this command continues until the accumulator goes below 0. And we've specified our test data here, and you can see actually our test data down here. This was the test data we transferred. So we filled the first 8 bytes of that range with the move next command. Then what we did is we pointed to the end of the range here, and we transferred another 8 bytes, but this time we used the move previous command, and you can see here we have now filled the last 8 bytes of the range whereas before they still had the random data in them. So we can use those now to quickly transfer blocks of data using the 65816, which is very nice. These commands did catch me out though, because I didn't realize that they were altering the bank register, which is the currently selected data bank register, and that was playing me up rather badly. So yes, that's something you need to just be aware of. So that's the rather nice new block move command. And the last thing we're going to be looking at is absolute longs. And this is again relating to the new 24-bit functionality. So in the same way as before, we might specify a 16-bit value to load from a 16-bit address rather than a direct page address or zero page address. We can now do the same with long 24-bit values, and we've got one just here. So let's just run this and let's see what we can do now. So here we're specifying memory address 030200 here, and what we're doing here is we're loading the accumulator from there. Now you can see that value here is 6162 at that address, and so that's been loaded in here, 6261, little endian, so it's become reversed there. So we've loaded in directly from that address just by specifying the full 24-bit address there. Now that's just specifying the address, absolute long as it's called, but we can index this. Here we're using the X register as an offset here. The X register is 1 on the first example, so we are effectively adding 1. So instead of loading in 6162, we would load in 6263, and you can see that's been loaded in just there when X was 1. We then set X to 2 and we load in again and we get 6364. And of course 6364 is offset by 2 from the base that we specified of 03200 here. So we can use the X register as an offset there from our absolute 24-bit address. And of course the only disadvantage with this addressing mode is we're using quite a lot of bytes. There's 1 byte for the command there, and then there's 3 bytes for the address. So if we were doing lots and lots of these commands, maybe we'd prefer to use the direct page in some way or something. But as I say, we now have the flexibility to be able to do that. Now, like with the direct page, we can also load long addresses from absolute addresses. So here we're using our square brackets and we're specifying the address long test here. And at long test, we've specified a 24-bit number here, 030400 here. And we are going to effectively do a long jump to that address. A long jump is a 24-bit jump. So we're jumping to a 24-bit address and we're loading that from the address long test. So what have we got? Well, we've basically copied this small test program to that address, and all it does is it loads 6666 into the accumulator, does a long jump to the monitor, and then it will do an infinite loop and just basically lock the machine. So if our long jump works, then basically we will jump to this address, and we have copied our test code to that address with the move next command here. That you can see here that the code has been transferred. You can see the 6666 there in memory at 030400, and we've then used our jump to the long indirect address long test there. That's loaded in the address, and the result is that the accumulator has been set to 6666. Now, as I say, that's a bit of a synthetic example, but it's a nice, easy way of showing this being used. You can see we were able to load the address here and then jump to that address using the JML command. Now, as I said before, you can go to my website and download my cheat sheet in which I've got all of these new weird and wonderful commands and also all these new addressing modes, including the old ones. So if you're not familiar with them all and you're not really that familiar with 6502, or if you're like me and you keep forgetting them, then cheat sheets are a really helpful thing for you. But the one thing I would always recommend with this kind of thing, the permutations of commands and valid addressing modes just get a bit weird. So it's best for you to just try things out yourself. As I said before, go to my website, download the build scripts and the source code, and then you can hopefully run these and check them out and just actually see things in action, because that's the best way of confirming things work, figuring them out in your head, and understanding it all. As I said before, if you feel you need to brush up on your 6502, please go on Amazon and buy my book. It's a nice way of supporting my channel. It allows me to keep working harder on crazy new content and covering more and more CPUs, because it's a struggle to do it. Anyway, I hope you've liked this. If you have, hit the like button, hit the subscribe button, and you'll see the third and actually final episode in the 65816 experience. I've already got 6502 tutorials on my website if you've not seen them, and I've also already got 502 based Super Nintendo tutorials. So that's something you can already see, but we're going to be looking at the 65816 Apple IIgs later on in my platform specific series. We're going to look at that system, and at some point we'll be looking at the Phoenix C256 as well, which is a 65816 hobbyist made computer, which is one of the few 65816 systems out there. So if you're interested in that, please hit the subscribe button, and I'm sure you'll see those at some point in the future. Anyway, I hope you found this interesting. Thanks for watching today, and goodbye.